And we're good to start. So this section is all about organizing data. Okay, so most of the time when we get data, it's going to be an assemblage or a collection of just numbers. And those numbers usually pertain to something that we're studying. Imagine that we were collecting, I don't know, these numbers look like they're in the ranges of 45 to 80 something or another. So these could be like the ages of a bunch of people that are considering retirement soon. I have no idea, right? These are just random numbers, random data that has been thrown at us, and it's been collected from somewhere. That data that's been collected is called raw data, okay? It's raw because it has not been processed or organized, not processed or organized. And we really can't make sense of the data until we process, organize, arrange, summarize that data, okay? And one of the ways we do that is by figuring out what the frequency distribution of the data set is. Frequency distribution, okay? So a frequency distribution is just a fancy way of saying that we're going to organize the raw data in
Wait, can you go back up for 1
in
second?
table form, yes. Okay, using classes and frequencies. Here, the word class means like we're going to categorize or lump together those numbers, right? The numbers that are close together, we're going to say that they're roughly in the same class. Okay, we're going to break up the data and organize it in that way into different groups. And then the frequencies is literally just how many times those values occur in the data set. So in other words, you have a bunch of random numbers here, at least to our eyes, they seem like they're randomly assembled numbers. We don't know where they came from, but it does constitute a data set. Some of those numbers are in the 40s, some of them are in the 50s and 60s. It looks like we have a really small number here, 27, right? But to make some sense of these numbers, what we will do is create classes or categories to lump some of the similar numbers together, okay? And we will create a frequency distribution that will look something like this. So essentially, these classes are going to be the categories here. Like we might say, we're interested in the numbers that are 27 to 35. We want to lump those together. The numbers that are 36 through 44, lump those together, and so on and so forth until we get to the highest number. So the numbers 90 to 98, right? So if we go back to the data set, you might see, okay, what is the smallest number that occurs in this data set? And it might take you a little while to sort through that. If we just look, I pointed out that this 27 is really small. So we know that's the smallest value. Is there anything smaller than 27 in this data set? Doesn't look like there's anything else in the 20s, right? And then we might say, okay, well, what is the largest number? We scan through this, we're in the 40s and the 60s, the 80s. We have a 92 here, but do we have anything higher than 92? We just scan this. Is 92 the largest?
Yes.
Looks like 92 is the largest value. Okay. Now, notice how tedious it is. So like literally scan, like using your eyes to scan row and column of this thing to see what is the largest number and the smallest number. Your brain is trying to hold on to the smallest number as you look at other numbers. So this is what we mean by like, I think that Trudy said that this class, ramps up in terms of difficulty really quickly. And I think that it's because when we're sifting through data, it's just really tedious. So like every process in statistics tends to be like tedious unless we have some way to automate it. And so if you saw what I had uploaded to Canvas yesterday was how to use the calculator. Like we could type in these 50 values into the calculator and then use the functions in here to sort the data from from smallest to largest in ascending order, right? That would make it very quick. The computer, provided that we typed in the values correctly, the computer would be able to sort that data for us quickly. We can easily just scan up to the top number, which would be the smallest, and then the bottom number would be the largest, right, using that function. But in lieu of using that technology, we just have to scan with our eyes. Okay, so these are the groups that we said are lumped together into classes or categories. And when you're trying to find out the frequency of data points or data values that fall into this category, we say, okay, well, are there any numbers in the data set between 27 and 35? Okay. So we can go back to the data set, and if you're doing this sifting by hand, you would scan the entire data set and then count. You would literally just count how many of these values fall between 27 and 35. And it turns out that if you do that count, only one of the values, that 27 that we were looking at, occurs in between these numbers. So we say that that class limit has a tally of 1. So there's only one value from our data set that is in that class limit and within those class limits. Does that make sense?
Yes.
Okay, so just to double check this, let's pick an easy one here and just verify that it's correct. So let's look at the class limits 72 and 80. According to this table, there should only be 3 values in our data set that fall between 72 and 80. So let's look at our data set. Okay, 72 and 80. Gonna scan. We're looking for 72 and 80. Something that falls in there. 72, 71 is too low, right? 72 and 80. Have I skipped anything? We have this one, right? 76. That's between 72 and 80. Okay, that's one. 72 and 80. This one's between 72 and 80.
You missed that 75, yeah.
And 75 is 72 and 80. 72 and 80. Is that it? That looks like it's it. 72 and 80. Right, so there's only 3 values here. So we can make a tally and literally count. And we see that there's only 3 of those values. So we'll say that the frequency with which this class occurs is 3. Okay, does that make sense? So it's a literal count. And that's why this is tedious, among other reasons, right? Maybe listening to my droning, slow voice is putting everybody to sleep. So let's go ahead and move on. Okay. So we're still looking at this same frequency distribution. It turns out that for this class, between 27 and 35, we have 1 value there in our data set. Between the next set of values, we have 3, 9, 15, 10, 3, 7, and so on. But the sum of all of these frequencies, when you add them up, should be the total number of data points that we have. Okay. So if we just double check this, right? According to this frequency table, if we have 1 plus 3 plus 9 plus 15 plus 10 plus 3 plus 7 plus 2, and I think that's everything, we should get 50. Okay. So this right here is going to be the total number of data points. Okay, so if we were to go back up to that array, that grid of numbers, if we flip back to this page, it looks like we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rows, 1, 2, 3, 4, 5 columns. So that means that 10 times 5 tells us that there are 50 numbers here. Okay, and that makes sense. If our frequency total here does not add up to the total number of values, then that means that we double counted something, or maybe we undercounted something. So you have to make sure that that all lines up. Okay. A way that you can sort of visualize that frequency distribution is just by stacking the tally like this. Sometimes, I don't know the name for this exact plot here, but sometimes when you write up the data as a dot, you might have like a dot here, and then 3 dots for the next class, right? So this is 1, this is 3, this should be the 9, and so on and so forth. You could organize the data visually. To see which of these classes has the most data points. Okay. Okay, and the only thing that I was getting at is that another way, instead of using tallies, is that you could put dots to count things, and then you might call that a dot plot. Okay, not super important here, but that would be is equivalent to our tallies that we've sort of laid on its side and we've stacked them up so we can see the height, right? The height of the tallies tells us which values are more frequent. Does anybody have any questions there? Okay. Well, there are 2 types of frequency distributions that are used most often, and that is categorical and grouped frequency distributions. So what we just looked at was numeric, and we sort of took that numeric data and we lumped them into categories. They're still numerical categories, but we don't necessarily have to have numbers. We can also have nominal data or ordinal data. So one example of that would be something like blood types, right? So if we're talking about blood types here, in this particular example, 25 Army inductees were given blood tests to determine their blood type. This is the ABO blood group. And we can construct a frequency distribution. In this case, it would be a categorical frequency distribution of these data, right? So here, we can say, okay, these are not numbers, but we can still count how many people have type A blood versus type B blood, AB blood type, and O, right? So what we could do is count them, right? Since the data are categorical, discrete classes can be used. What are the blood types? Well, we have 4 blood types, right? A, B, AB, and O. And just for good measure, this data set seems pretty small. How many people have type A blood in this data set?
Five.
Looks like 5 to me, right? What about B?
Seven.
Looks like 7. Type AB?
4.
Looks like 4. And type O?
9.
Yeah, looks like 9 to me. Okay, so what is the total number of data values that we have here? Well, if you don't want to do the math, you could just read the example, right? There should be 25. But do these numbers add up to 25? We have 5 and 4 make 9. That would be 18. 18 plus 7 would get us 25. Okay, so that means everything is okay. We're good to move on. You always want to make sure that you properly counted things, because when you're, again, staring at a data set or raw data set like these, your eyes are going to go cross-eyed. You're going to miss something, or you're going to double count something. It happens all the time. Okay. Does anybody have any questions about that so far? I think that frequency distributions are pretty straightforward, or counting up the frequencies. Okay. Well, then we might want to organize that data into a table like the one that we were looking at before, right? This is going to be a categorical frequency distribution, and we're going to organize this into different classes. Now, here the classes that we have are categorical. That is, they're not numeric, so we don't have to worry about lumping, the similar data values together. So for step 1, we're going to make a table with classes in column A. So this is going to be our class column, and the class is just going to be the label of each of these blood types. So type A, B, AB, and O. Doesn't really matter what order you put those in. What matters is our tally, right? Had we counted this thing with a tally, which I sort of think is a little bit unnecessary. Maybe you don't have to make column B with a tally, but we said that there were 5 people in the data set that had type A blood. So you might tally this up as you're counting through and say there are 5 there. Okay, you might say that there are 7 because we counted 7 there. We counted 4 AB and counted 9. That's 5. 1, 2, 3, 4. There's our tally column, right? Just to make it look similar to the table that we looked at before. But the frequency is the most important thing, right? That's what we're really interested in. We just counted those up. We said this was 5, this is 7, this is 4, and this is 9. Okay. We also noted that the total here should be 25, as was recommended by the example at the very beginning. It said that 25 people were tested, so we should get a frequency, total frequency of 25. That's how many data points we have in our data set. And then this extra column that we have here in step 4, it says find the percent of the values in each of the classes. Okay, now this is really important, because what we're going to do is sort of think about, okay, well, I know that there are 5 people in this data set that have type A blood, but what proportion or what percentage of the data set does that make up? Okay, so we can say, well, it looks like most people are type O, so they should make up a larger percentage of the entire data set. And the way you find that percentage is the way you calculate any percent, right? So whenever you're calculating a percentage, right, you might have learned this in grade school, you always do the part divided by the whole, right, or the part divided by the total, and then you multiply that by 100%. Okay, so there are 5 people out of a total of 25 that have type A blood. So what we can do is 5 divided by 25, and then multiply that by 100. Okay, I'm going to throw that into the calculator so we don't have to worry about it. 5 divided by 25, right? The part that we're looking at, the type A blood, divided by the total number of people in the data set. Go ahead and get that, and then multiply whatever that is times 100. Okay, so we have 20% of our data set has type A blood. Does anybody have any questions about how to find that frequency percentage? Okay, we can go ahead and do the same process for the rest of these. So 7 divided by 25, and then we'll multiply that by 100. We'll do 4 divided by 25, and then multiply that by 100. And then 9 divided by 25, and multiply that by 100. Okay. So if I go ahead and do these, I won't show them on screen, but I'll write the final percentage. That should be 28%. 4 divided by 25 times 100 gives us 16%. And 9 divided by 25 times 100 gives us 36%. Okay. Now, the nice thing about these frequency distribution tables is that, like I said, this should be the total number of data points. But if we're adding up percentages, they should add up to 100%, right? If we counted everybody correctly, then that should constitute 100% of all of the data. So if I add 20 plus 28 plus 16 plus 36, that should always give me 100%. So just another way to check yourself is to add up those percentages, and you should get 100 if everything is counted correctly. Does anybody have any questions there? Okay. So moving on to grouped frequency distributions, these are used when the range of the data is large. Does anybody know what I mean by the range of the data?
The highest sorry, so the highest in the lowest numbers?
Yeah, exactly. So it's like if the range of your data is large, that means that the data itself spans a large set of numbers. So technically, if you wanted to calculate how wide the data set is, then you would take the largest number and subtract the smallest number, and that would give you the range. Right? It tells you how widely spread out the data is. So range you could think of as how widely spread out the data are. Okay. So when we're trying to organize that data, we want to think about the smallest value and the largest possible value in the data set, and then consider those the lower and upper class limits. We're going to create boundaries for these groups, or lump the data together and then have different boundaries or categories for similar values. Okay, so if we turn our attention to this table here, you'll see the first column says class limits. Okay, so I don't know if this pertains specifically to, I don't think that this pertains to that first data set that we looked at. I think that they just randomly had generated some data here. But from a total of 50 values, they were able to break those values into these categories, right? The numbers 58 to 64, right? 65 to 71, and so on and so forth. They're going to create these things called class boundaries, which will capture the data values. We'll talk about that in a moment. And then you can go back into the data set, make your tally, and then get your frequency distribution. Okay. But let's talk about class limits a little bit more. Okay. Okay. So, well, now I'm curious actually where they got these numbers from. I'm pretty sure it's not from this raw data, because we have a value of 27 here, right? So this is just a randomly accessed data set that they've organized here. Okay. Smallest and largest possible values are the lower and upper. So we know that this 58 has to be the smallest value in the data set. And the largest value has to be this 106. I'll write it here, largest value, and nobody can see that. There we go. Can I zoom out? There we go. That's a little bit better. Largest value in the data set. Okay. So that's going to start off our class limits, the lower limit and the upper limit. And then we really need to figure out how these class boundaries are constructed. Okay. So to find the class boundary, we need to average the upper class limit of one class and the lower class limit of the next class. Do you guys know how to take an average? Like the average of two numbers?
Yes.
How do you do it?
You add them together and then divide by how many there are.
Yeah, that's exactly right. Okay, so typically if we just have two numbers and you needed to find an average, then we would take, I'm going to put x1 plus x2 and then divide by however many numbers there are. So if there are only two numbers here, then we'll just add those together and then divide by 2. But in general, an average is going to be a bunch of numbers, right? x1 plus x2 plus, and we can continue doing that. And then n here is going to be how many numbers there are. We're going to talk more about averages later. For this particular thing, if we're just trying to find our class boundary, right, because they've already established these classes, then the class boundary is found by taking the upper class limit of one of the classes. So this is the upper limit of one of the classes, right? And this one's the lower limit. Okay. So we're taking the upper limit of one of the classes and then the lower limit of the next class. So go down to the next class and find that one. So we need to average these two numbers. When you find the average of 64 and 65, let's go ahead and do that here. 64 plus 65, divide that by 2 because it's just two values. What we'll end up getting is 64.5, which is how they found this value here. And so that's basically how they constructed all of these. If we took 92 and 93, for instance, and found their average, we would get 92.5. So again, I could throw that in the calculator. We took the upper limit of one of the classes and then the lower limit of the next class, 93, add those together, divide it by 2, and that's how we get this class boundary. Okay. So just some rules. The class limits should have the same decimal value as the data, but the class boundaries should have one additional place value and end in a 0.5. So that means that if the class limits, that is, if the data are all whole numbers, that means that they're all expressed to the ones place, right? There's no decimal values. Then that means the class limits will not have decimal values, okay? But the class boundaries will have one additional place value and they will end in a 5, okay? It's very similar to one of the rules that we saw in chapter 1. Okay. The class width for a class width, That is how wide the class is. So the class width for a class in a frequency distribution is found by subtracting the lower class limit from one let's see. The class width for a class in a frequency distribution is found by subtracting the lower or upper class limit of one class from the lower, these typos are really throwing me off, from the lower or upper class limit of the next class. Okay. Class width, sort of a new concept here. Okay. So we're going to take the lower class limit of one class from the lower class limit of the next class. Okay, so there's a couple of ways that you can calculate this. And so this basically summarizes the different ways you can calculate the class width. So based on this definition here, we're saying that if you look at the class limits 72 and 79, these are both the lower class limits of these two classes, right? If we were to subtract those, what is the difference between 72 and 79? If you subtract 72 from 79, what do you get?
7.
7, right? So if I look at 79 minus 72, then I get 7. So according to this definition, we should have a class width of 7. But here, the workbook is saying, okay, we could do successive lower class limits or their boundaries, and we should get the same class width. So if we look at the class boundaries and subtract these successive boundaries, maybe it's going to be harder to do because they're decimal points. We could take 71.5 and subtract that from 78.5, but we should be getting that same value of 7. So 78.5 minus the lower boundary above it, 71.5, and we get 7 as well. Okay. So again, these are just different ways to obtain the class width, how wide the class is. Okay. Another way that you can find it is by taking the upper and lower class boundaries. So if we go to one of the classes and subtract these, it looks, just by eyeballing it, 78.5 minus 71.5, that looks like a difference of 7 also. There's another concept that we might need to be aware of, which is the class midpoint. And midpoint can be calculated by averaging the upper and lower class limits or boundaries. So here's a formula for class midpoint, and it's just taking the lower limit and the upper limit and dividing by 2. So the midpoint is literally the middle point between two values. And if you thought about their position on the number line, then that's what we were sort of thinking about as the midpoint. So just as an example, we could find the midpoint between 72 and 78 by averaging them, right? So 72 plus 78 divided by 2, we get 75. And sure enough, 75 is positioned right in between those class limits, right? It is the midpoint of those classes. Does anybody have any questions about that material?
So I had a question.
Yeah.
So how do we set the class limits, like from 58 to 64, from 65 to 71, from 72 to 70?
That's a good question, and we're getting to it in just a second, right? It really depends on the data set, because like we're gonna encounter some data sets that will have different values, right? And the different values will have a different range, right, based on the data set, based on the number that we're given. And so it's really going to depend on the numbers that we're given. So let's go ahead and just move on, because I think that we're going to answer your question here in a moment. Okay, as we work through an example. So first, let's just lay out or break down all of this stuff. Okay, so this is the same data set that we were looking at. So let's just lay out what the rules are here. When we come up and we're confronted with a data set, we're going to have a bunch of numbers that we're looking at. When we start to create a grouped frequency distribution, we want to make sure that there are at least or somewhere in the range of 5 to 20 of these classes, right? We're going to lump all of our numbers together so that we have 5 to 20 different groups. Okay. Class width should be an odd number, as we saw in the last example. As we saw in the last example, the class width that we calculated was 7, and that's going to be the case for most of these examples. I want to say all of them, but I'm always really reluctant to say all. Okay. But doing so, having these class widths that have an odd number is going to ensure that the midpoint of each class has the same place value as the data. Okay. That means that when we calculate the midpoints of our classes, if we're dealing with a data set that's all whole numbers, then the midpoints will also have whole numbers or also be whole numbers. Okay. The midpoint is literally the numeric location that's in the center of the class, right? The class is determined by these two values, the lower limit and the upper limit. The midpoint's right in between them. Okay. And we're going to learn about these graphs called histograms, and we're going to use the midpoint for constructing those histograms in section 2.2, right? So that's the only reason why we're introducing the midpoint formula right now. Okay. If the class width is an even number, then the midpoint will be in tenths. That is, we'll end up with a decimal value. A single decimal point like 8.5 or 15.5, right? There will be one decimal point or one place value after the decimal. Okay. Another rule for our classes and grouped frequency distributions is that the classes must be mutually exclusive. That is that they don't overlap. So the data, like one data point, can't be placed in multiple classes. It's either in one class or another, but it can't be in both. Okay. The classes must be continuous. That is, even if there are no data points, once we construct these classes, it might be the case that, for instance, let's go back to this example over here. Let's say that we're collecting the data of all of our ages in this class. We might not have anybody, I don't know if that's the case. We might have some people that are between the ages of 10 and 20, but if, for our examples purposes, there was nobody in this age class between the ages of 10 and 20 in this class, then we would put a 0 for that frequency, right? We still need to keep this class, even though there's a frequency of 0, that there's nobody that has that age in the class. Okay? But usually we won't start our, if this is a 0 out here, we won't start the frequency distribution with a 0. So let's say that we have 10 people that are in this age range. Just gonna make this up. Let's say we have 5 people in this age range. Maybe we have 13 people in this age range, but we don't have anybody that is, actually, let me think about this again. Let's say we have 13 people in this age range, but we have 0 in this age range. Well, we need to keep this class, even though we have a frequency of 0 there. Okay, that's what's meant by the classes must be continuous, right? Even if there are no values in the class needs to be included in the frequency distribution, right? And this usually goes for the classes that are in the middle of the data set, right? Not necessarily on the end, right? Because when I started off that example, I said, what if we didn't have anybody in this age range? Well, certainly we wouldn't start our data class limits with this age category, because we didn't have anybody there, we would probably start here instead. Okay. So when we construct our limits, that's what's going to start us off, and then we'll start to break that down into the classes based on those limits. Okay. The only exception occurs when the class with the 0 frequency is the first or the last class. There we go. Right. So you don't have to include them if it's the first class at the top of the table or at the bottom of the table if it has a frequency of 0, because like, why would we include that? In any case, the classes must be exhaustive. There should be enough classes to accommodate the entire data set. We shouldn't have any data values that are above or below the class limits that we set. And then the classes must be equal in width, except for open-ended distributions. But I think for our case, in our examples here, they're not going to be open-ended distributions. So equal width. That means that every class has the same width. So if we looked at one of our other tables, we calculated, for instance, that the class width of this particular data set was 7, right? The difference between 72 and 78. Sorry, is that right? Did we say that was 7?
Yeah, it was 7.
72 to 78.
But we used the class boundaries.
We use the class boundaries. So here we said that's 7. Right. And right, the way you calculated the class width is from 72 to 79. And so that's a difference of 7, right? So this is 7, this is 7. And that's why I said, as we moved into like 86 and 93, the difference between those values is also 7. The difference between 93 and 100 is also 7. So across these classes, they have the same width. Okay. So those are the rules that we have to sort of keep in mind as we engage with these problems, these practice problems. So these are the essential steps that you'll have to follow as you do the homework problems in Connect Math, right? We need to determine what the classes are, and we do that by finding the highest and lowest values. We're going to need to calculate the range. We already established that the range is equal to the largest value minus the smallest value. We need to select the number of classes desired. We're going to see how we go about doing that. Then we're going to find the width by dividing the range by the number of classes and rounding up. Select a starting point. Usually the lowest value in our data set is going to be where we start off our classes as we construct them. And then we're going to use the class width to sort of create our next set of classes, right? Find the upper limits, find the boundaries. Then once we have our classes constructed, which this is the big bulk of the work here, then we can start to tally the data. Once we tally the data, we'll find the numerical frequencies from the tallies and then find the cumulative frequencies, and that's related to the percentages, okay? So I know that last class on Monday, I totally blew through the entire lecture without giving us a break. So do you guys want to take a 5 to 10 minute break right now?
Yes, please.
Yeah, let's go ahead and take a break. Get up, get some water, do what you got to do, and we'll come back at 1:32. Resume recording. Okay, so we're back. So we have our procedure for creating a frequency distribution, and we're going to use that stuff to graph. Eventually, we're going to be graphing our data. But for now, really, we want to just go ahead and do our frequency distribution. So this example gives us a data set that has, it looks like record high temperatures for each of the 50 states. And we need to construct a grouped frequency distribution using 7 classes. So they're giving us the instructions here. We need to use 7 classes out of these 50 pieces of data, right? So the first thing that we need to do is look through the data and sort of assess what should our classes be? How should we construct them? And the way we make that determination is by first looking at the highest and the lowest values in the data set. So if you just, run your eyes through these rows and columns of numbers, can you see what is the lowest value here in this set of 50 values?
100.
Yeah, I'm pretty sure it's 100. So we'll go ahead and highlight that one. And we know that this is the smallest value. Okay, does anybody know what the largest value in this data set is?
134.
134. Now you guys must have really fast eyes, because it would take me a while to comb through this, and then I'd be confused and sort of think to myself, well, maybe I missed something, and so I'd comb through it again. But sure enough, 100 and 134 are respectively the smallest and the largest values in the data set. Okay, so now that we have those values, we're going to use those to sort of construct the rest of our frequency distribution. So the first thing that we're going to need to do is, what is the range of our data here, right? How widely spread out is our data set? Okay, so we'll just take the difference, right? 134 minus 100 gives us 34. That's the range of the data set, right? Which is established here. And again, the range is how wide the data are spread out. Okay. Another way that we can calculate the width of our classes, because we're constructing those classes, is by taking the range of the classes and then dividing by the number of classes. In this particular problem, they said use 7 classes. So now that we have the range, we can divide that by 7 and get 4.9, right? But we don't want to be using decimal points to construct our class widths. We want to use whole numbers, so we're going to round this to the nearest whole number. So 4.9 rounds up to 5. So we're going to say that our class width are going to be 5. Is everybody okay with that?
We always do that when it's a decimal.
Yes, ma'am. We want our class widths to be whole numbers.
Okay.
So now, once we've done that, we're going to select our starting point for our data. And it makes the most intuitive sense to just start from the lowest value, right? We said our lowest value was 100. And then we'll go up from there by adding our class width to get the lower class limit of the next class. So we're going to add the class width to the lower class limit to get the next lower class limit. Okay, so that means that if we were filling this table out, we would start with the lowest value here, lowest or the smallest value. And then to get this next class limit, right, the next one, lower limit for the next class, we're just going to add the width. So we're going to put 105 here. Does that make sense? Add the width. And then we'll add the width again to get the next class. So if we add the width, we should get 110, then 115, then 120. And this should be 125, right? 125. 130. And we want to go all the way up to our highest value. This class should go from 130 to, I believe we should just end at 134, right? But we're just setting those up. Then as we move on, the first upper class limit, so if we look at the first class here, this upper limit here, which is blank, is just one less than the next lower class limit. Okay, that's a lot of words. In simple terms, if this lower class limit is 105, then this upper class limit should be one less than that, or 104. That makes sense? If this lower class limit is 110, then this upper class limit before it should be one less, which is 109. Is that a little bit clear? So what should this upper class limit here be?
114.
114. There we go. And then this one should be 119, right? And then this one should be 124. And another way that you can just, once we've established this, we know that the class width, if we're looking at the lower limits, are just going up by 5s. Once we've established one of these upper limits, you can just use the width and add the width to get to the next one. So if we added 5 here, we would get to 109. If you add 5 here, you get to 114. Add 5, you get to 119. Add 5, you get to 124, and so on and so forth. So we could just add, that class width, or you could just do that whole trick where you take 130 and say this should be 129, right? And then this thing should end with our highest value, which we said was 134. This is our highest value. That makes sense?
Yes, sir.
So we need the range. We use the range to find the class width. We start off our classes with the lowest data value, and then we can start constructing our lower class limits here by just adding the width. Then we can construct our upper class limits by just subtracting 1 from the next lower limit, right? Once you have one of those set up, you could just add the class width to get up to the next value, right? Okay. Now, as far as constructing the boundaries, that's our next step, right? We need to figure out how to do this. Now, the class boundaries are going to be midway between an upper class limit and the subsequent lower class limit. Okay, what do I mean by that? Let's go ahead and move to the next page. Notice that we filled this out already. We got our lower limits already, and then we use those to construct our upper limits. And now we want to fill out our boundaries. This says that the class boundaries are going to be midway between an upper class limit and the subsequent or the next, right? Just to put it in simpler terms, the next lower class limit. Okay, so we can take our upper limit here and then the subsequent lower class limit here, and we need to find the midpoint between these two values. Okay. So the class boundary that we're going to look for, if we take the average between 104 and 105, right, we can throw that in our calculator if we're not clear on how averages work, right? Or, you might be able to, some of you guys might be able to just eyeball those two numbers and say the midpoint is this, but we can find the average, get the midpoint at 104.5, right? And that's how we calculated this number. Okay. Now we're going to take that, and that's going to be our upper boundary here, 104.5. And if that's the case, then we're going to take, if you remember our technique from chapter 1, we're just going to go down half a point, right? So instead of having 100 here, right, since that's our lowest data value, we sort of want to go a little bit wider than that and go down to 99.5. Right, and the idea here is that we want to capture our lowest value, which is 100, but make our data point or our class boundary here, the lower boundary, sort of capture the lowest value, but extend out a little bit. And then also we want our class boundaries here to be the same, right? If we take the difference between these two numbers, it should be the same as the class width. So if you were to calculate the class width from these boundaries, as we established in the rules before, 104.5 minus 99.5 should be the same class width that we had before, right? So if you weren't sure, and you didn't want to use that rule where we just said, okay, let's just subtract this by 1 and then throw a 0.5 at the end of it, you could just take this number here that we calculated by finding the midpoint and then subtract the width, and you would get this value. Does that make sense? And this is sort of going to ensure that, again, our class boundaries are mutually exclusive. So all of our data values are going to fall in between these class boundaries, but our class boundaries sort of have decimal points, right? So there's never going to be a data value that's on one of these boundaries. It's always going to be on the inside of the boundaries. And that's sort of why we're constructing them this way. So we can start off the next boundary by saying this is 104.5. And we could use the class width here to find what the upper boundary is going to be. Because we're just going to add the 5, right? The class width. And we could just go down our lower boundaries and then our upper boundaries now using that class width. So if we just added 5 to this value, maybe we'll bring our calculator into the mix, 104.5, and let's just add the class width here. We get 109.5, right? And that's about half less, right? 0.5 less than 110. And we can just add 5 to that to get the next one up, which is 114.5. Add 5 there, get 119.5. Add 5 there. But you might already establish the pattern. Add 5 there and be able to figure this out more quickly. Right? Those are all of our lower boundaries. Then we can just go to our upper boundary over here, 104.5, and then just add the class width. Plus 5 gives you 109. But we've already sort of calculated these, right? If that's 109.5 here, then this should be 114.5. This should be 119.5, 124.5, 129.5. And then if we added 5 to that, 129.5 plus 5, 134.5, right? And again, we know that our highest value is 134, and that's going to be captured in the middle of these class boundaries, right? None of our data values are going to be on the edges or on the boundaries themselves. Does anybody have any questions there? Seem pretty straightforward?
Yes.
Albeit a little bit tedious, right? Okay. Now is the real boring part. Because once we have the class limits set up and the class boundary set up, which is something you're going to have to do in the homework, then we need to actually look at the data and then tally up how many of those values fall within these class boundaries. Okay. Now, I'm not going to take the time to physically count them right now because they're already counted in the workbook. So I'm just going to zoom into the next table here. And it looks like they've already been counted by a small child, right? So now we just need to count up our tally so that we can get the frequencies. So again, I would say like, you don't have to do these tally marks. You could jump right into the frequency distribution unless the problem is specifically asking you to take the tallies. I wouldn't bother with the tallies because you're counting them, write the number down, right? So you might omit this column. Okay. But now let's go ahead and count up those tallies since they've done it so conveniently for us. The frequency of data points that fall in these class boundaries is 2. Then this should be 5, and that is 8. This is 5, 10, 15, and then 3 more, which is 18. 5, 10, and then 3 more, so that's 13. 5, and then 2, that's 7, and then we have 1 and 1. Okay. Is everybody okay with that?
Yes.
Cool. Right, so again, before we really move on to the next part, we want to make sure that these frequencies, that the total adds up to the total number of data points that we had in our data set. So how many values do we have in our data set? Does anybody remember?
50.
There should be 50, right? So just to check and give yourself some peace of mind, let's go ahead and add 2 plus 8 plus 18 plus 13 plus 7 plus 1 plus 1. And that's 50, right? So that checks out. That means that we didn't miss anything. Okay. We just really want to be thorough when we're combing through the data because it's very, very easy to lose some stuff. Okay. Is everybody okay with this? Well, the next part of the table just says that, okay, we counted everything correctly. I'm pretty sure that this is what we got: 2, 8, 18, 13, 7, 1, and 1. But sometimes we want to come up with a cumulative frequency distribution. So we're going to add this column over here to our table. And basically what a cumulative frequency distribution is telling you is that this distribution shows the number of data values that are less than some specific data value, less than or equal to. Okay, what do I mean by that? Let's think about this for a moment. Less than or equal to. Okay, if we think about the upper boundary here, what we're saying is that there are 2 data values from our data set that fall between 99.5 and 104.5. You could go into the data set and you could verify that for yourself just by counting how many numbers, how many data values fall between these 2 numbers. Okay. Or you could say that 2 of our data values are below this number, right? That would be the same thing. So when we start off our cumulative frequency distribution, it's going to start off very similar to our frequency distribution. We're just going to copy that 2 over. And this is like we're saying that 2 of our data values are less than 104.5. Okay. But then as we move up in our cumulative frequency, we're saying, okay, well, how many data values are less than this value, 109.5? Well, if this is the upper part of our class boundary, that means that these 8 data values have to be below this number, right? So you might feel tempted to just put 8 here. But these 2 data values are also below this number 109.5. So what we'll do is say that if we're considering our entire data set and asking how many data values are below 109.5, it's really 10 of them, because we need to add up all of these 8 values that are below 109.5. And then these 2 values are also below 109.5. So we have 10 values that are less than 109.5. Oh, put the decimal down wrong. 109.5. Does that make sense? So in other words, as we're considering, how many data values are below 114.5, we're going to take this frequency and add it to all of the frequencies before it. That's what we mean by cumulative, that we're adding all of the values that are below it. So technically, the number of data values that are below 114.5 are these 18 data values plus 8 plus 2. So at that point, you might say to yourself, well, I'm feeling a little bit lazy. 18.8 plus, I'm sorry, 18 plus 8 plus 2 would just be 28. right? And I could have just taken this 10 here and then added it to the 18 and gotten the 28. But I think that it's probably more instructive to say we're adding up everything that came before this category or before this class. So now what should the next value in our cumulative frequency column be?
Mm, 41.
Is it 41? Because that goes up to 31. And then, yeah, it looks like 41 to me. And then what should the next value be?
49.
49. And the next one?
50.
50. And the next one?
$51.
Looks like it should be 51. That can't be right. Did we mess up somewhere?
I think so.
Maybe I added incorrectly somewhere, right? Because the cumulative frequency should just
41
I
and
think
41 and
yeah.
7.
41 and 7. Oh, should have been 48, right?
It should be, yeah.
There we go.
Yeah. 41, 48, 49.
Okay, so that's a way you could check yourself, right? At the end of your cumulative frequency table, you should be getting all of the data values, right? So that should be the total of 50. Okay, so then if we added 7 there, that should have been 48. That was a very good mistake, very instructive. I love it. Okay, then we added 1 to that, which was 49. And then we added 1 to that, which puts us at our 50. And that's how it's done. Okay. So like I said, you know, you might want to come back and revisit this video as I put it up on Canvas. And they are in the Canvas modules. But the rest of this workbook just walks you through the layout for what the homework problems will look like in section 2-1. Okay. So if you follow the instructions that we've sort of set out in this first example, you should be able to tackle those homework problems. If you run into any issues, as always, you can send me a message and remind. But I think I want to give you guys a chance to work on those homework assignments as opposed to listening to me sort of go on and on about it. Okay. So if you have any questions for me, you're more than welcome to hang back and we can chat a little bit. But otherwise, you guys are free to go and I'll see you on Monday.